John Lewandowski.
Thanks very much. I'm John Lewandowski, and to give you a sense of some of the background where I came to use standards, I was an undergraduate and did all my degrees at Carnegie Mellon, and as part of that, I did a co-op program with an oil company, and I was stationed in the oil refinery doing material selection and then some failure analysis. And that transpired into some graduate work where I used a number of ASTM standards to look at how materials fracture in a very systematic way. And then I wanted to go overseas, so I did that in England and learned that there's different standards over there. The British standards may be a little bit different. They're similar, but not identical. But I worked on pressure vessel steels there and aluminum pressure vessels for both the nuclear as well as energy storage. And then I came to CASE, and I'm in material science and engineering, but I'm also a secondary appointment in mechanical because of my interest in the material side, but then also how they behave mechanically, fracture and fatigue. And so when you look at the kind of things that I've been involved with, I'm interested in processing materials, what kind of structure that results in, and then what kind of properties. And all of those have ASTM or other standards associated with them that we've been using on a variety of different materials in the bubbles. And in the bubbles, you'll see that we also work on automotive and aerospace, biomedical and defense, and most recently, the whole area of additive manufacturing and 3D printing. And so as part of that, our students publish lots of papers, and in particular, I want to highlight a couple of review papers that are being published on fracture and fatigue of biomedical materials that Janet Gabor is putting together. And then you'll hear a bit later about Mohsen Seifi, who's doing mechanical behavior of 3D printed materials, using these kind of standards to start to look at the kind of properties that you can get. The other thing I want to introduce to you is that we have lots of laboratories at the university. Top class equipment, millions of dollars worth in many cases, that are run by staff that'll help to train you on them. And so you should take advantage of these. There are a number of these listed here. There are certainly more, but they all use standards to some extent. Now, the one that I'm going to focus on is the Advanced Manufacturing and Mechanical Reliability Center, because that's the one that I'm involved with. And we use this in the classroom. We're not on any of those ships, fortunately. This is a representation of the Titanic. And in these cases, we do tests in the laboratory to mimic the conditions that you might have in impact. And so some of the tests that we do in the laboratory are on notched bar impact testing. And as you can see here, there have been experiments done on the actual Titanic ship steel, not by us, but by others. And they compared that to modern ship steels. And what you're plotting on the left here is how much energy that material absorbed when it fractured. And so the RMS Titanic plate is shown here, and how it changes with temperature. And then a modern hull plate is shown there. And you can see it's quite different. That was the best steel that existed at the time. And you can see that it's quite different than what exists now. And so we use those kind of things in the laboratory to demonstrate how materials change with time, but also how they change with temperature. And certain ones will do this very dramatically. We also do things in tension and in other quasi-static loading conditions, but the impact ones are really kind of exciting, so I like those, and that's why I showed it. We also do failure analysis, and this is at the graduate level, and this was brought up earlier. This is a class we teach and have been teaching for quite a while, and we introduce the engineering concepts that are used in this. And in these cases, we also use standards to look at the chemical analysis of some of the materials or their material properties, as I just described, and we invite people in from the Case Law School, the faculty, to explain this to students also from that side and that perspective. Now, if I look at the research use of these kind of standards at the graduate level, then I'll highlight some of Janet's work again, where she's putting together this fracture and fatigue of wires and cables used in the biomedical industry. So this is quite a large review, hundreds of papers that she's looked at and gathered information where tests have been done using these various ASTM and other standards. And the idea here is that wires and cables are used in lots of different biomedical applications. And the way those wires and cables can be configured is quite different, as you can see on the right. They can be used in heart pacemakers. They can be used in electrode stimulation in things that have been done here and pioneered here at CASE on functional electrical stimulation. And they can also be used in stent kind of applications. So the reliability of the material is very important and how you characterize it in a systematic way. In addition to this, there's lots of work going on now in additive manufacturing, 3D printing. And so the idea here is, now then, rather than machining a sample, print the sample or print the component as long as you have the CAD model that you can do it with. And there are a number of evolving ASTM standards now that are coming to the forefront here, one of which you'll hear from Mohsen Sefi shortly. So the inset here is showing actually a biomedical component. And the idea here is, as long as you have the CAD model, you could build this layer by layer by selectively melting powders in certain regions and then build up that structure. This will continue to go through, as you'll see in a second. So this is being done on biomedical components, and what's being done here is the powders are being melted layer by exposure to an electron beam. This is a cartoon representation of each of those powders melting, but you're essentially doing this layer by layer and then building the structure, as you'll see in a few seconds. Other industries are also using this now. Aerospace is starting to fly components. These are not fracture critical components at this point, but they are getting experience with them, both on the polymer side, and as recently announced by GE, a jet nozzle for fuel injection has been designed that could only be made this way. And so the question in all these cases is, once I have those components, what are their properties? Are there standards that are evolving that we can use to evaluate them? And so the answer to that is yes. You'll hear more about that from Mohsen in a few minutes. In this case, you can see that the samples that have been made are embedded in a powder, and then those finally come out. The key thing here is that they can be made with a porous surface that the bone can grow into. And so the other work that you'll hear are from Mohsen, and this is some work that we're doing with the America Makes projects. Same idea, where you use now an electron beam, and we're going to make a sample now, an ASTM type bend bar that we can test in a controlled way. So now, rather than making a component, we're going to make a test sample. And so in this case, layer by layer, the sample is built, and then eventually we're going to test it. Now, we brought some of these with us that you can see afterwards if there's any interest. But the idea in this case is, if I build one of these things, are the properties going to be different if I build it in these different orientations? And so that's what Mohsen is investigating here, and we're testing it in different orientations to see if the properties are different. Lots of interest in this area right now. And so I'll leave you with this, that in conventional materials, we know how to characterize them because we can test them in all these different orientations. In these new evolving areas, like additive manufacturing, this is still evolving. And the properties have to be evaluated in these different orientations, and having something that you can point toward, a standard that will help you do this in a systematic way, is very important. And so that's the thing that I'll leave you with. Mohsen will pick up a little bit more on this later. Thank you.
Thanks, John.